Today, I'm going to show you a non-real way of solving the Fresnel's integrals, but I'm not entirely sure if this is legitimate or not. But anyway, check this out. We are going to investigate this integral first. And notice, this is almost like the Gaussian integral, but we just have the constant a right here, and a we want it to be positive constant. So, what we are going to do is, first, we are going to write it so that we have e to the negative parentheses squared like this, and I just have to enter square root of a times x. Once we have this, we can just do a quick use up. Put u equal to square root of a times x. Differentiate both sides, and then divide the square root of a to both sides. And now we can take this integral to the u world. Notice, when x is negative infinity, if you put it here, this thing has to be positive, right? Because a is a positive real number or a constant. And positive times negative infinity, we just get negative infinity. So u starts at negative infinity. And then if you put infinity to here, u will go to infinity. And then right here, we just have e to the negative u squared. Dx is du over square root of a. And we can put the 1 over square root of a on the outside. And then we have the integral, negative infinity to positive infinity, e to the negative u squared du. And notice, the u right here is just a dummy variable. This is just going to give us square root of pi. So, we'll just have 1 over square root of a times square root of pi. And that's the answer. Okay, great. Now what though? Well, I told you we are going to use something non-real, so let's check this out. So now, we are going to be using our imaginary friend, I, and I will plug that into the a right here. So we have the integral going from negative infinity to positive infinity, e to the negative I x squared dx. And based on this formula, we should just be able to plug in I into the a's right here, right? So that's square root of pi over square root of I. And now, look at the bottom here. We can actually simplify this a little bit. And of course, the easiest way to do that is to use the polar form. So, let me just go ahead and look at the complex plane. This is the real, and this is the imaginary axis. I, let me say it's right here. Let's write I into the polar form, and to do so, we need the distance from the origin to this point, and that's just equal to 1. And we need the angle from here to here, and that's pi over 2. Polar form is r e raised to the I theta power. R is 1, so times e to the I theta power. So, square root of I is the same as, inside here, e to the I pi over 2. And for the square root, we can just write that as the 1/2 power. Now multiply the powers, we get e to the I pi over 4. Then use the Euler's formula, we will just get cosine of the angle plus I times sine of the angle. In order to end up with the answer that we are about to get, we just need to do this. And this is just the principal value for the square root of I. And of course, we can simplify this. That's 1 over square root of 2. So is that. Okay, so we have square root of pi over, they both have the same denominator. The top is just 1 plus I over square root of 2. And now we can simplify this a little bit more. Here, we can put the square root of 2 on the top times square root of pi over that denominator, 1 plus I. Then we can multiply the bottom and the top by its conjugate. This is going to be 1 squared minus I squared, which is 1 minus negative 1, which is just a 2. So, square root of 2 times square root of pi times 1 minus I over 2. And now, square root of 2 and 2, they can reduce to just a square root of 2 on the bottom. So all in all, we will have, let's distribute it, we get square root of pi over square root of 2. and then distribute it minus I square root of pi over square root of 2. So that's what we have. What do we do next? Well, notice this part, we have e to the I theta. So we can utilize the Euler's formula, and this will be equal to integral going from negative infinity to plus infinity. I'm looking at the negative x squared as the theta, so we will have cosine of the theta, and that's negative x squared, plus I times sine of the theta, which is negative x squared. And now we can simplify this a little bit. We have the integral going from negative infinity to plus infinity. And because cosine is an even function, so the negative doesn't matter. And I'm going to close this integral. And for sine, it's an odd function, meaning we can take the negative on the outside. I'll put it right here. And then we have a constant I. Let me keep it here. And the integral, negative infinity to infinity, sine of x squared. Now, ladies and gentlemen, this right here, it's the real part of this integral. And then the result for that integral is this, and this is the real part. So that means this must be equal to that. And then for the imaginary part, which is this part, well, along with the negative, yeah, but that's also a minus, so they match perfectly. So this has to match with that. Therefore, we can conclude that this right here must be square root of pi over 2. Likewise, this right here must be square root of pi over 2 as well. And that's pretty much it. And now let me tell you guys about my concern. Earlier, in order for us to come up with this formula, we had a condition on A, that is, A is greater than 0. Right here, if I want to use this formula, here we have the I. Can we really say I is greater than 0? I don't think so, because the only thing I know is I is less than 3u. So is this true? This is not true actually. So is that approach really legitimate? I don't know how I should feel about it. We do end up with the same answer here and here. So you guys can leave a comment down below, let me know what you think about this approach. Alright, that's it.